Hello, welcome to this new lecture of the course Transportation Network Analysis. So, we had discussed some differences related to user equilibrium and system optimization. In the last class, we had seen Brice paradox. So, we will now discuss about a new concept today called price of anarchy. So, we know that for a given network, the total system travel time, or in short TSTT, will be the least for SOS compared to user equilibrium. Okay. And that is obvious because in the objective function of system optimization, we try to minimize this total system travel time. So, whatever value we get for total system travel time from that formulation, that can never be larger than what we get from the user equilibrium. Okay. Now, the question is that is it possible to claim that the total system travel time of the user equilibrium flows is at most X percentage worse than the total system travel time of the system optimization formulation. So, the question is in a way that how much further the total system travel time that you obtain from user equilibriums can be larger as compared to the system optimization. Okay, if we can kind of provide some bound that, for example, this total system travel time from user equilibrium flows will not be more than say 50% than the total system travel time that you obtain from system optimization, something like that. So that we kind of get an idea that how much this total system travel time can deteriorate, because in the real world the flows are more closer to user equilibrium because everyone wants to try to minimize their own travel time. So that's why we want to compare how much performance we get with the UE flows while determining the total system travel time as compared to the system optimization formulation, which gives the best total system travel time, but that is not realistic. Okay, so Tim Ravgarden had addressed this question. So he's a researcher. So in this paper, how bad is selfish routing, he had addressed this question that can we say anything related to the bound on the total system travel time of user equilibrium as compared to the total system travel time of system optimization. So let TSTT UE and TSTT SO be the total system travel time corresponding to user equilibrium and system optimization respectively for a given network. Okay, so this TSTT UE is the total system travel time that you obtain when the flows are getting distributed based on user equilibrium, and TSTT SO will be the total system travel time that you obtain when the flows are getting distributed based on system optimization. So this price of anarchy, or in short POA, is defined as the ratio of TSTT UE by TSTT SO. Okay. Now you can guess that this value has to be larger than or equal to 1 only, because the total system travel time is minimized for the case when you have system optimization formulation. Now, Tim Ravgarden had proved that for linear and non-decreasing travel performance functions, this price of anarchy is at most 4 by 3. Okay. So if you assume that the travel time functions are linear, then this price of anarchy is at most 4 by 3. That is, the total system travel time that you will be getting from user equilibrium will not be more than 4 by 3 times the total system travel time that you obtain from system optimization. Okay. So this is a table that shows these bounds given different forms of the link performance functions that we assume. So all of these are discussed in more detail in this paper, how bad is selfish routing. So of course there is a proof behind all of this. Okay, so this result that the total system travel time obtained from UE will not be exceeding more than 4 by 3 times the total system travel time of SO when the link performance functions are linear. So that has to hold in every case, for every network and so on. Okay, for every kind of flow that you can think, I mean every kind of demand and so on. So since there are infinite such possibilities, it is not possible to verify all of them. So then there has to be a mathematical proof for that. So since there is shortage of time, so we will not discuss that proofs here, but we are just providing some values here that for linear link performance functions, this price of anarchy value is approximately 1.33. Then for quadratic link performance functions, it is 1.626, and so on. So you can see that as we go from linear to cubic here, these ratios kind of increase. Okay, that is, as the link performance functions are becoming higher order functions, this price of anarchy bound increases. Okay, and this is the case when the degree of all the link performance functions is less than or equal to p, then this is the bound that you get on the price of anarchy. Okay. Okay, so with this now, we'll be shifting towards the discussion of optimization algorithms. So we have seen the optimization formulations for user equilibrium, we've also seen the optimization formulation for the system optimization. But the issue is that even though the solutions, for example, that are obtained from the first order conditions of user equilibrium or system optimization, they are in fact the optimal solution. But the thing is that solving those equations becomes very complex when the network is very complex and so on. Okay, so that's why we need efficient optimization algorithms that can solve these formulations of user equilibrium and system optimization when the problems become very complex. So we'll be seeing some theory related to optimization algorithms for these kind of problems. So this is saying the same thing. So traffic assignment problems such as user equilibrium and system optimization can be formulated as equivalent optimization problems, and therefore we need to discuss efficient ways for solving them. So we'll be first starting the discussion with the focus on one dimensional minimization. So we have done something like this before also, that when we were discussing about KKT conditions, that is first order conditions and so on. So in order to have a basic intuition of what is going on, we usually sometimes start the discussion on one dimensional optimization problems and so on, and then we extend it to larger dimensions. That is, this one dimensional minimization is the case when the objective function is just varying with one variable. Okay, and then we look for the case when it varies with more than one variable. So what we mean here is that we want to solve this optimization problem, that we want to minimize this function zx in the interval a to b here. Okay, so this function z is only varying with one variable x here, and since it is restricted to lie in this region a comma b, this is a constrained optimization problem. Okay, that is, we have these constraints that x is greater than or equal to a and x is less than or equal to b. So these are the constraints, and we want to minimize this function zx. Okay, so we'll be assuming some regularity conditions that x lies within some finite interval a comma b, and that zx is continuous and uniquely defined everywhere in that interval. So these conditions will ensure the existence of a finite minimum of zx for some x in a to b. Okay, so why are we discussing this? Because it is important to understand that all of these results that are being presented, there are some underlying assumptions that this function zx is continuous and uniquely defined everywhere in that interval and so on. So for the purpose of our discussion, we will also assume that there is a single unique minimum of this zx function in a comma b. So such functions are called diatonic functions. Okay. So let us first focus on interval reduction methods here. So what are these methods? So in interval reduction method, we focus on a portion of this initial interval a comma b at the nth iteration, and this interval at the nth iteration is denoted by an comma bn. Okay. So in the interval reduction method, I mean, initially if we have this interval a comma b, then at the nth iteration we will be focusing on some subset of this interval, which will be represented by a n b n. Okay. So at each iteration of this interval reduction method, the interval is divided into two parts here. The part in which the minimum cannot lie and the current interval for the next iteration. Okay. So the part in which the minimum cannot lie is discarded and the procedure is repeated for the new current interval. Okay, so what we will be doing here is that we will be dividing this initial interval into uh, into various parts as we will go along. So for example, initially when we start from a comma b, so then we will be saying that some part of this a comma b, we are sure that the optimum will not lie, so we will then discard, and then we will be focusing on a shorter interval than before. Okay, and again in the next iteration, in that shorter interval, we will be again saying that some portion of this we are sure that the optimum will not lie, so then we will be discarding that and so on. Okay, so as we will go along in this interval reduction method, the interval that we are focusing on will keep on reducing. Okay, that's why the name is like this, that it's an interval reduction method. So suppose we start designating this a comma b as the first interval. Okay, so since n is equal to 0 in this initial case, so a0 is a and b0 is b. Okay, so let the size of the current interval at iteration n be denoted by in. Okay, so let Rn be equal to in plus 1 by in. Now you can guess that since we are reducing the interval size in each iteration, so this Rn has to be less than 1. Only in that case in plus 1 will be less than in. Okay, and we will be considering this case that the reduction ratio is a constant for all the iterations. So in every iteration we will be working with this fixed reduction ratio equal to r. Okay, so for the first case, this in will be equal to b minus a, because for first case n is equal to 0, so I0 is equal to b minus a. So the interval reduction methods are typically terminated when the size of interval of interest is less than a predetermined constant. Okay, so when we realize that the size of the interval that we are focusing on has become very small as compared to some threshold that we had decided before starting this optimization problem, then we can terminate, because then we are sure that the optimal solution will now lie in this small interval. So there is no point of further keep on continuing, because we are fine with this estimate of the optimum that we have here. So the estimate of x star, so x star is suppose the optimal solution, so the estimate of x star is then the midpoint x bar of the interval after n iterations. Okay, so suppose we decide to stop at after n iterations here, so then we will be having this interval a n comma b n. Okay, so we do not know where actually the optimum x star lies in this interval. Okay, so to remain on the safe side, what we will be assuming is that our estimate of the optimum solution is the midpoint of this interval, that is an plus bn by 2. Okay, so this is the estimate of the optimal solution that we get after n iterations. Okay, now if the optimum must lie within a tolerance of plus minus epsilon, that is x star must lie within x hat plus minus epsilon, then the number of required iterations can be calculated. Okay, so this epsilon is some constant that is given before, that is we want to make sure that the optimum solution x star should lie within x hat plus minus epsilon. Okay, so with this information actually we can calculate what is the number of required iterations for this. So the number of iterations n is then approximately equal to this. Why we are saying approximately equal? Because the number of iterations has to be integer, so that's why um, the actual number of iterations will be plus minus 1 around this. Okay, so this discussion is also uh, mentioned as a question in the book by Joseph Sheffield on urban transportation networks. So it is not very difficult to estimate this n here. Okay, so I'll leave this as an exercise here, that if someone has to suppose determine this, then how will you determine this? So the question is that suppose you have this initial interval I naught. Okay, now you know that there is a reduction ratio r. So I1 will be equal to what? I1 will be equal to the length of the first interval I naught times r. Okay, so in that way you can write that this In is equal to what? It is equal to I0 times Rn. Okay, how do you get this? Because you know that In is equal to In minus 1 times r, and In minus 1 will be equal to what? In minus 2 times r. Okay, so when you keep replacing this, you will be getting this. Okay, and what we want is that this epsilon, this In, should be less than or equal to 2 epsilon. Okay, so now when we do this, that I naught times Rn is less than or equal to 2 epsilon. Okay, so let us take Rn less than or equal to 2 epsilon by I naught here. Okay, and suppose let us take log on both the sides, so you get n log r less than or equal to log 2 epsilon by r naught. Okay, now one thing is that this r is less than 1. Okay, so this will actually be greater than equal to sign here, because this log r is a negative quantity. So n will be greater than equal to log 2 epsilon by r naught divided by log r. Okay, and which is the same as log 2 epsilon minus log r naught divided by log r. So this is how you get actually, although I had left this for you to derive, but I have actually also derived it here. Okay, so this is not very difficult to derive here, and we are writing this approximately because n has to be greater than equal to this. Now if this is not an integer, so then you have to round it off to an integer value. Okay, so various interval reduction methods differ only in the rules that are used to examine the current interval and to decide which portion of it can be discarded. Okay, so we'll be seeing different kind of interval reduction methods, and the way they differ is that how they examine the current interval and how they decide on which portion to discard and so on. So this golden section method is one such interval reduction method. So this is based on comparison of the values of the function zx at 2 points x ln and x rn, where xln is less than xrn. Okay, so these xln and xrn will obviously be lying in this interval a comma b, and in fact at the nth iteration they will be lying in this interval an comma bn. Okay, that we are focusing on. So let us consider this example here. So suppose we are trying to minimize this function zx here, and we are at the nth iteration. So the boundaries of the interval that we are focusing on are a and b, and suppose there are these 2 points xln and xnr. Okay. In this figure that is shown here, it is shown that the objective function at xln is greater than the objective function at xnr. Okay. So the minimum must lie to the right of xln, as we assume that zx is diatonic. Okay, since we are assuming that there is a single minimum in this interval, and it is already known that the objective function value at xln is greater than the objective function value at xnr. So therefore the minimum has to lie on the right side of xln, on this side here. Okay, and therefore this interval an comma xln can be discarded. Okay, so there is no need to focus here. So this is the portion of the interval that we will be discarding. Okay, so that's why in the next iteration we can focus on this interval that remains xln to bn, which is what is being shown here. So the new interval an plus 1 comma bn plus 1 is this. So new an plus 1 is the same as xln, and bn plus 1 is the same as bn. Okay. So the essence of this golden section method is the rule used to choose xln and xnr given an interval an comma bn. Okay. So how should we choose these xln and xnr given this interval an comma bn? That is the main task here. So to reduce further function evaluations, one of the interior points is obtained from the last iteration. So when we have already established what an plus 1 and bn plus 1 will be, we have now determined these two interior points xl n plus 1 and x r n plus 1. Okay. Now in order to reduce the function evaluations, what we will be doing is that one of these interior points xl n plus 1 will be kept the same as one of the interior points as before. Now this has to be equal to this x n r here. Okay, because this xln has already been equated to an plus 1. Okay. So in this case, this is what it is saying, xl n plus 1 is equal to xnr. Okay. So therefore now we need to find what will be x r n plus 1. Okay. So x r n plus 1 will be equal to n plus 1 plus r times b n plus 1 minus n plus 1. Okay. Where r is this ratio root 5 minus 1 by 2, or approximately equal to 0.618. Now how did this ratio come? Okay, so this is what we will be looking at derivation here. Okay. So in each iteration x and r is 0.618 of the interval length to the right of an. Okay. So x and r is what? It is 0.618 times this bn minus n plus an. Okay. Similarly, xnl is 0.618 of the interval length to the left of bn. Okay. Now the question is, why r equal to this root 5 minus 1 by 2 or 0.618 is special? Because this is the only ratio that will ensure that in this example x n l plus 1 can be used as x n r. Okay, that is, this point is exactly the same as this one here. Okay. So let bn plus 1 minus an plus 1 be equal to r times bn minus an, where r is the interval reduction constant. Okay. Now this bn plus 1 minus n plus 1 by bn minus an is equal to this, because we have already set this, that bn plus 1 is the same as bn and an plus 1 is the same as xln. Okay. So since we already know that this is equal to r and this term is equal to this, so we have this thing here. Okay. And one more thing that we know is that if we do 1 minus r here on both the sides, here and here, then we will be getting this here. Okay. That is Bn minus xn r by Bn minus An is equal to 1 minus r. Okay. As xn r is equally distant from Bn as xn l is from An. Okay. Now note that Bn plus 1 minus xl n plus 1 by Bn plus 1 minus An plus 1 is equal to r. Okay. As xn plus 1 l is r of the interval length to the left of Bn plus 1. Okay. Now note that Bn minus xn r is the same as Bn plus 1 minus xl n plus 1. This length is the same as this. So now we can equate these two expressions. This is a very important step here. So then we will get this here. Okay. So this is the equation that you get. So this is one equation that we had, and previously we had one more equation, okay, in the last slide. So when you will be equating that and assuming that I is equal to Bn minus An, so then you will be getting this relationship here. Okay. And when we solve this r square plus r minus 1 equal to 0, this is the positive solution of this equation. Okay. So the name of this golden section method is named after this ratio root 5 minus 1 by 2. Okay. So with this we will be ending the lecture here. Thank you.